resistor. And I get some straight line. Suppose I connect for this resistor. Suppose I connect a 2-volt battery. If I connect a 2-volt battery across this resistor, I'm going to have this much current. So if I apply a voltage V1, I'll get a current I1. Suppose somebody else applies a different voltage, V2. We're going to get some current I2 across that resistor. Some voltage V2 across it, we'll get some I2 through it. So the effect of applying a voltage V1 is to give a current I1. The effect of applying a voltage V2 is to give a current I2. That's like the effect of Sean, the effect of Edgardo. In fact, maybe instead of V1 and V2, I'll just to keep the analogy going, I'll call it Sean and Edgardo. So there's the current Sean, the current due to Edgardo. Now I hire Sean and Edgardo at the same time as my voltages across this resistor. So the combined voltage across this resistor will be the voltage of V Sean plus the voltage of V Edgardo. So that combined voltage would be that plus that, which would be about this over here. Vs plus E. So it's Vs tacked on to VE. What current is going to result? The current that will result will be this current up here, which is I Edgardo plus Sean. And I'm going to try to convince you that for a resistor, the current of I Edgardo plus Sean is equal to the current IS plus the current I Edgardo. And I get that combined, the current of the two voltages combined is indeed the current if I added the effect of just V Sean plus the effect of VE. What do you think? Convinced or make sense for a resistor? Let me now, maybe it'll make even more sense if I show you an example where it doesn't work. So you can see, okay, see why it kind of works there. Let me go to a second device. I'm going to plot the current as a function of voltage for a diode. You made this graph in one of the early labs. What you saw was that the graph looked like this. Okay? So now we're going to apply V Sean, V Edgardo. We can spread that out a little bit more. Okay, let's make this. What is the current if I apply just the voltage V Sean? What current do I get roughly? Looking at the graph.
0.
If I apply just V Edgardo, what current do I get looking at the graph? Close to 0. So if I use the principle of superposition, what current would I expect if I applied a current of V Sean, if I applied a voltage of V Sean plus V Edgardo? If I got 0 current for V Sean and 0 current for V Edgardo, what would I expect if I applied that combined voltage of V Sean plus V Edgardo? I'd expect 0. Now for the diode, do I actually get 0? Well, V Sean plus V Edgardo would be this voltage over here. Which doesn't give me 0. That voltage gives me about 1 amp. So in the case of a diode, if I look at the current I got from just that voltage, plus the current I got from that voltage, they'd both be 0. So if I looked at the effect of both of them combined, I would be expecting 0. But I actually don't get 0. I get 1 amp. Over here, they did add up. So if V Sean, if I put some values on here, so V Sean will be 2 volts. V Edgardo will be 6. So the combined would be 8. Let's say this current is 1 amp. That would be 3 amps. And that would be 4 amps. So in the case of the resistor, the current I got from V Sean was 1 amp. The current I got from V Edgardo was 3 amps. The current I got from both of them will be the combined 4 amps. So for this resistor, the principle of superposition works. For the case of the diode, the principle of superposition does not work. In the case of the resistor, you would say that a resistor is a linear element. The diode is not a linear element. One thing to be careful on as you start to become a little more sophisticated with your math skills, you start to use this term linear systems, linear differential equations. You start to see this word thrown around. There's a temptation sometimes to think that linear means straight line. No. Linear, we're using in this context to mean if I double the voltage, I get to double the current. Linear, what we mean is if I add the effect of VE plus VS together, those combined effects give me the correct answer. Here's an example of a graph where your normal definition, what you might think of linear is not, does not work out. Suppose I had some funny component, some odd resistor that looked like that. Instead of a straight line starting at the origin, I have a straight line starting here. So in this case, the effect of V Sean would be 2 amps. The effect of Edgardo, let's see if I've got this. So 2. The slope is a half. So 1, 2. So this should now be. Sorry, my picture's gotten a little confusing. 2.5 amps. No, before, sorry. Yes. Before. So I would expect the combined, if I got 2 for Sean, 4 for Edgardo, I'd expect the combined to be 6. What is the combined, actually? 5. It would be 5. So I'd be predicting 6, I'd actually only get 5. So by taking this curve and shifting it up, I make it no longer linear in what we mean by that term. So it's a little different than what we just mean by a straight line. So linear doesn't mean straight line. It means that these effects add together. Basically, this principle of superposition is valid. It's valid for linear systems. The resistor is a linear component. The diode is not. The op-amp behaves like a linear component. A capacitor and inductor, the other two components we're going to deal with at the end of this, or starting today through to the end of the semester, are also linear components. In fact, this course is sometimes entitled Linear Circuit Analysis. Here in SUNY Ulster, we don't call it that. We call it, I think we just call it circuit analysis, something like that. So we don't put the word linear in the title. But sometimes you'll see that term linear in the title to mean this kind of effect works, and we can use the principle of superposition. Okay, I promised you that I thought you would like this.